This is one of the weirdest kinds of goodbye in astronomy. Because this isn't a comet returning, it's a speck we'll likely never see again. And the scary part is, the proof isn't some dramatic image. It's one number hidden inside a grainy streak. If that number is just a hair above a line, it means the object doesn't belong to the sun at all. And once astronomers saw it, they stopped, reran the orbit, and realized we weren't watching something arrive, we were watching something leave.
You're looking at real telescope footage of a speck sliding past the stars. Why did this faint blur make astronomers stop and run the numbers twice? Because its path doesn't loop like our comets. It doesn't loop at all. Stay with me as we test one idea. If its orbit is hyperbolic, it didn't come from here. I'll show you the exact clues hidden in this grainy track, and the moment scientists realized we had to say goodbye. By the end, you'll be able to tell a bound ellipse from a getaway arc at a glance. In the grainy footage, the stars stay pinned like thumbtacks while one dim point creeps across the frame. That slow slide looks ordinary until you fit its motion to an orbit and the math refuses to close the loop. Teams saw that and reopened their solver because a path that doesn't curve back hints at a visitor passing through, not circling home. Here's how the night unfolded. An Atlas scan flagged a mover that jumped more pixels between frames than the usual main belt crowd. Automated software posted coordinates with timestamps, and within hours observatories started chasing it. You get a relay, short exposures, precise times, and quick reductions so the next telescope knows where to look. Each data point is a line in space and time, and those lines build the first sketch of an orbit. Early, that sketch is wobbly. You lock the camera on the stars for one sequence, then switch to track the object itself, and every strategy leaves a fingerprint in the images you use to measure speed. At first, the numbers could bend two ways. With only a handful of measurements, you can force a stretched ellipse that takes decades to loop around the sun, or a hyperbola that never returns. The uncertainty bars were big enough to allow both. Give the solver 3 nights, and it will draft a preliminary orbit, but those nights carry traps. If you stamp a frame a fraction of a second off, or if you mix observatory clocks that drift by a small offset, the fit can flip from bound to unbound. That's how sensitive an early orbit is when the arc on the sky is short. You judge the shape with one number, eccentricity. If E is less than 1, the path is elliptical and closed. If E is exactly 1, you're on the knife-edge parabolic case. If E is greater than 1, the track is hyperbolic, open, and the object is a passerby. As more follow-up arrived, the best fit E for this object edged past 1 and stayed there while the formal uncertainties shrank. That trend matters. A single solution can hop above 1 by chance. A sequence of solutions over added nights that keeps E above 1 and tightens the error bars points you to the same answer from different angles. Think of it like throwing. Toss a ball too slowly and it arcs back. Throw faster and it climbs higher but still returns. Throw past escape speed and it never comes down. Earth has its own escape speed, and so does the sun if you consider orbits around it. The orbit fit is telling you the throw speed in space. This one cleared the bar. The images themselves helped. When you track at the sidereal rate, stars are sharp and a fast object smears into a tiny dash. When you track at the object's rate, the target sharpens and the stars trail. The length of those streaks and their angle across the sensor give a second, independent sense of how fast the object moves relative to the sky. Night to night, the slope of that streak changed the way a fast, inbound object should. But the clincher wasn't only the shape. The key was the velocity it carried far from the sun, before solar gravity had a chance to speed it up. That excess speed, the part you still have at infinity, should be 0 for anything bound. Once the fit locked, the eccentricity stood above 1 by a margin that cleared the noise, and the hyperbolic excess velocity came out positive. That means the footage you're seeing caught an object already moving too fast to belong to a looping family, with the numbers stable as more nights came in. So the orbit doesn't close. The motion checks out in the images, and the math gives it leftover speed. The next question is where that approach hyperbolic excess speed, the infinity? Second, from what direction does it enter, the radiant? And how does that compare to the local standard of rest, the average motion of nearby stars and gas? Those two pieces turn a noisy trail into a passport check. Now the hard part, could our own system fake it? Giant planets throw objects around all the time, and the Oort cloud feeds long-period comets on nearly parabolic paths. But those ejections tend to top out near escape conditions. You get something that behaves parabolic, with V infinity close to zero once you account for the sun's pull. It might be slightly positive or negative based on how you fit the arc, but it hugs the line. For this object, the measured excess speed stayed meaningfully above zero as the observational arc lengthened. When you subtract the gravitational boost and look at what's left, you're not seeing a near miss. You're seeing leftover speed that doesn't vanish at large distance. Think about how that happens. Jupiter can pump energy during a close pass, yet even strong kicks usually convert a bound comet to barely unbound. The numbers gravitate toward E just above 1 and V infinity that whispers, not shouts. Here, the excess speed spoke clearly. That contrast matters because it rules out a one-off planetary slingshot masquerading as interstellar. A local origin would need a very specific encounter chain and still would struggle to sustain a solid positive V infinity once you fold in more nights of data and reduce the uncertainties. There's also the frame of reference. Early fits often use heliocentric elements, but the sun moves in the galaxy and the planets tug. For interstellar checks, you switch to barycentric fits, which reference the center of mass in the solar system. That cleans out the biggest periodic wiggles from planetary pulls. With a barycentric solution, you track how the parameters evolve as the arc grows. Does the eccentricity stay above 1? And do the error ellipses tighten? The covariance matrix tells you how sensitive the elements are to each other. If E and V infinity wobble together when you add data, you distrust the result. If they stabilize, you gain confidence. In this case, successive fits converged rather than drifted, which is what you want when you're making a claim about origin. Air traffic control offers a useful mental check. If a radar sees something inbound at an angle and speed that doesn't line up with any runway, holding pattern, or standard arrival, controllers know it didn't depart from a nearby gate. Same here. The radiant did not point back to the typical corridors that feed cometary traffic, and the speed profile didn't match a local departure. You can see it on the sky. Plot the path through the constellations and watch how it bends before and after perihelion. Each side of closest approach tightens different pieces of the orbit, inclination and the longitude of the ascending node. As those locked in, bound solutions fell away. They required contortions that the data didn't support. The outbound leg brought a last practical gift. Solar elongation grew just enough to grab final imaging runs before the brightness slid under reach. Those late frames extended the arc and cut the errors again. So the proof stacked up from multiple angles. V infinity above zero by several standard deviations, a barycentric eccentricity that stayed greater than 1 across infinite fits, and an approach vector that didn't align with our known reservoirs. That's why we can say it's from elsewhere without hedging. We've pinned the origin. The real lesson sits in the narrow window between discovery and fade out, where timing, coverage, and a few clean timestamps can turn a faint streak into a story about how often the galaxy drops a calling card. A faint smear on a sensor can carry a signature that spells elsewhere. Excess speed does that. When V infinity refuses to fade to zero, the track tells you it's not circling back. You can read that right off a calibrated stack of exposures. If you want more real-time sky guides and data dives, subscribe. If you have a scope and a steady clock, your follow-up astrometry on the next alert matters. Timestamps, measured positions, and quick uploads move the fit from guess to proof. Interstellar visitors don't loop for encores. We catch their story on the way through, but we never hear that voice again.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.